Hello students, my name is Sumit Sagar. I'm a PMR PhD student at IIT Palakkad. Today we are going to discuss lecture 3 of the live discussion section, in which we will cover lecture 11 to lecture 15 by Professor Ashok Desai, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion. First we will see some of the theoretical MCQ, and at the end I will just solve some of the problems. Okay. Okay, so the first question, gas turbine is also called as, okay, this is also called as combustion turbine. Okay. Because the after the combustion chamber only, the product gases will transport to the gas turbine. Okay. So uh, and there also the rest of the combustions are going to happen. Okay. So sometimes gas turbines are also called as combustion turbine because some residual fuels combusted. Okay. Okay. So so next is gas turbine is a type of gas combustion engine. Okay. Okay. Gas turbine is always a internal combustion engine. Okay, because combustion takes place inside the engine. Okay. So gas turbine is a combustion turbine, okay, and gas turbine is a internal combustion engine, okay. Let's go to the next question. Dash gas turbines are called as auxiliary power units. Okay, always remember the smaller size this gas turbines are called auxiliary power units. Okay, micro turbines are used to power the hybrid vehicles. Okay, these are very straightforward questions. Quickly we will go through it. Okay. The micro turbines are also known as the turbo alternators and generators. So jet engines are classified into dash types. Okay. Jet engines are classified into 5 types. What are those? I'll write down. One is a turbo shaft. One is a turbojet. One is turboprop. And one is the turbofan. And one is the prop fan. These are all 5 types of jet engines. Okay. Jet engines works on dash cycle. All types of jet engines and gas turbines are always works on the Brayton cycle. Okay. Gas produced can be varied by varying the fuel flow. Okay. So when the fuel flow increases, the energy produced by the engine is also going to increase. And when the energy produced by the engine is going to increase, then there is two things is also going to increase. One, there is production of higher thrust. Okay. And one more will be, there will be more production of exhaust gases. So the answer is C. Okay. So thrust produced also depends upon rotor dash. Okay. Okay. So here in this question, although this thrust produce having some impact on the blade surface, because if the blade surface is not that much smooth, then there will be a reduction of thrust produce. Okay, because there will be more drag. Okay, so the angle also having a played a very important role. Okay, but here in the question they asked what is the measure among all these, and because there is no all of the above options are also not there, the type of options are not there, so that's the reason we just choose which is the more uh, vital or more important in from all these options. Okay, or which will affect more the thrust produced. Okay, so the and the answer will be rotor blade pitch. It affects the thrust uh, much as compared to the other two parameters. Okay, because through pitch we can actually adjust the blade angle, we can actually adjust, and blade surface we are assuming is actually smooth. Okay, so yeah, just write down. Okay. Thrust radius depends on the rotor blade pitch. Okay, next is how many burners are placed in can annular combustors in gas turbine. Okay. Okay. So here this is a kind of theoretical question. Okay, but the answer to this question is it's not specific. It can be one or more. Okay, so be greater than one. Okay, greater than equal to one. Okay. Okay. Multiple or single burners are evenly spaced in combustor. Okay, and this is actually only used in gas turbines. The silo combustors are mounted internal to the gas turbine body. Okay. This is actually a false statement. It's actually mounted external to the gas turbine body. Okay. Turbine and output shafts rotate freely without any connection to the engine. Okay. This is actually a true statement. Okay. So turbine and output shaft is standalone in gas turbine engine. Okay. So it can actually rotate then. Without rotate freely without any connection to the engine. Okay. So when the amount of energy required is high, the life of the gas turbine is dead. Okay. That means if you are operating a gas turbine engine or any kind of engine under high load, then obviously the life of the engine is going to what decrease. Okay. If you are riding a bike and you are riding every time with heavy speed or it's like that, then obviously the life of the vehicle will be less. Okay. So there will be for sure there may be some problems, especially in the engine. Okay. Or you have to do regular maintenance all these things of the engine. Okay. So since load increases, okay, load on engine. In gas turbine, dash output igniters are used at the starting. Okay. So yeah, this output igniter means it is a kind of your in your bikes, by cars, spark plug. Okay, so similar to that. Okay, in gas turbine to start the combustion. Okay, this kind of high. We actually initially there people are using high output igniters. Okay, because the gases are not that much fuel efficient. Okay, so that's the reason why very high temperature igniters are required. But nowadays gas turbines are very working on very fine and very pure fuel. Okay, kerosene based fuel. Okay, aerofuels are there. Okay, so those are actually very highly combustible fuel. So yeah, we don't need that much high or high voltage igniters. Okay. So in the if in the question the starting what is not there, then if it is starting is not there, then the answer will be what? A. Okay, that is low. If it is not there, if now, but now answer is B. Okay, because starting what is mentioned. Okay. So when you are giving exam, read the question very carefully, because this one word can change the meaning of whole question and the options. Okay. So when gas turbine is required to operate continuously, then the power output is dash. Similar question we already seen, like here, like when the amount of energy required is high, the life of the gas turbine is less. Okay, going to decrease. In the similar manner, in this question, when the gas turbine is required to operate continuously, continuous means you are operating in a kind of a high load condition. Okay, you are not giving any break to the engine. Okay, so that means your power, whatever the efficiency or whatever the power output, because our power output is directly proportional to your efficiency of the engine. Okay, so because the whatever load you are providing continuously, that's the reason why your output power is going to decrease if you are operating the gas turbine engine continuously. Okay, so that's the reason in aircrafts you can see commercial aircraft there is actually halts are there. Okay, 1 hour, 2 hour, 3 hour halts. Okay, security check, and this all this in are there for the commercial aircraft. Okay, filling of fuel, there is no only filling of fuel, it's required actually little bit rest time for the cool down of the engine. Okay, in some gas turbines cavitations are dashed by using fuel cooled oil cooler. Okay, Cavitation is a phenomenon which is mostly avoided by any of the gas turbine engines. Okay, not only any of the gas turbine, any kind of engine, we have to avoid the cavitation. Okay, why we need to avoid? Okay, so that's what we now going to see. Okay, the answer anyway is A. We have to remove the cavitations. This question is actually kind of simple, because if you don't know anything also in this question, what fuel, cooled, oil cooler, all these things, if you don't know anything, if you see one word like in gas turbine and then one term is cavitation, okay, you don't know increased cavitation or not caused due to oil cooler, you see only the one word, that is cavitation, and directly you can choose the option remove. That's it. What's there, it's not, doesn't that much matter. Okay, by using something. Okay, so those things, because most of the questions are always to remove the cavitation. Okay, this is a kind of when in your exam you don't have time, you want to only guess, this is actually a best way to guess. Okay, still anyway we'll see the reason why it's there. Cavitation is required to be removed. Okay, now what does this fuel cooled oil cooler? Okay, okay, so fuel cooled oil cooler. Okay, that means the, because you see the name suggests everything. Okay, uh, okay, okay, okay. So now this cavitation always happens when there is cavitation is actually a fluid mechanics phenomenon, and it happens in a gas turbine engine. Okay, because of the presence of water vapors inside the fuel. Okay, so this is the cause of your cavitation in the gas turbine engine. Okay, now this fuel cooled oil cooler, what it do is, it will actually heat. Okay, it will actually, what it do, heat the fuel, because for fuel the thing is we don't need any kind of water contents. Okay, if you see actually in rainy days in your bikes, if you see there will be some water, just accidentally some water if you go into our petrol, there will be a kind of jerk in the when you are riding the bikes or any kind of vehicles. Okay, so that means is not, combustion is not that much proper. Okay, and there won't be that much energy is produced by the this our IC engines. Okay, so yeah, so what this fuel cooled oil cooler, this one device is there in the in the aircrafts, gas turbine engines. What it do, it just heat the fuel. Now when it will heat the fuel means the temperature of the fuel will what, going to increase. Okay, temperature of fuel going to increase. Okay, when the temperature of the fuel going to increase, there are also chances of evaporating some of the fuel. Okay, but one advantage will be, there will be chances of evaporating the what, water droplets. Okay, so water droplets also in the fuel is going to what? To evaporate. Okay. So when the what there that means this water droplets is going to what? Decrease. Okay. When the water droplets is going to decrease, then there will be a the chances of cavitation is going to what? Decrease. Okay. Okay. This is what the story. Okay. Let's go to the next one. Dash can be used as fuels in gas turbines. Okay. Okay. So all kind of diesel fuel, petroleum fuel, okay, can be used in the gas turbines, that we already know. But there are also one more thing, the natural gases nowadays. Actually liquid fuels are there. Are nowadays using. We are actually using some kerosene based fuels, especially it's a kind of mixture of all these petroleum and diesel products. Okay, especially kerosene based fuel system. Okay, and more you can see um, near to this aerodrome field, you can see Indian Oil having these kinds of fuels. Okay, aircraft fuels. Okay. But nowadays actually researches are going on for the gaseous fuels. Okay, and natural gases are there. Natural gases is one of the option, but with that also some of the fuels like hydrogen fuels. Okay, ammonia as a fuel. Okay, and methane actually nowadays rocket fuel. Many countries are using rocket fuel as methane. Okay, so slowly all these kinds of fuels are hydrocarbon fuels are or carbon free fuels are nowadays taking importance to use in the gas turbine engines. Okay, so researches are going on, and most probably near future, next 5 to 10 years, we'll see also gaseous fuels will be used in the gas turbine engine. Okay, which will be more efficient and it will be lightweight. Okay, as compared to these liquid fuels. Okay, so yeah, the answer is obviously D. Okay, so vanadium content in the fuels used for gas turbines should be dash. Okay. Okay, so when this type of question will be asked, what some different foreign particles. Okay, this kind of these are called foreign particles in the fuel. Okay, when these content they ask should be increased, decrease. Always if you don't know anything, you just always put the answer. It should be decreased. It should be low. Okay, that will be the option. Okay, if you don't know also that particle name, because that will be any in 0.001%, 0.10001%, that much percent it will be. Okay, so many particles will can be there. Okay, if you don't know them also, if they want, okay, this is this particle can be there, it should be what, high or low, always the option will be low. Okay, but still why that we also now going to see. Okay, so if that means if there will be increment in the okay, just That means if the vanadium content will increase, that means what will happen? The specific heat of the fuel is going to decrease. Now this specific heat is actually very much important parameter, because if the specific heat of the fuel is going to decrease, that means the energy produced by the fuel will be, or the output power produced by the fuel in a gas turbine engine combustor is going to decrease. That means at the end the efficiency of the gas turbine engine is going to decrease, okay, which we don't want. Okay, that means in very high amount of fuel you are getting very less output, okay, or you can then travel very less. So these are the some problems if we are going to, this vanadium content is going to increase. Okay, so gas turbine fuels congeal at dash degree are used in locomotives. Okay, locomotives means in your vehicles. What temperature? Okay, congeal is a term which means in what temperature the fuel will freeze. Okay, and the gas turbine fuels like your petroleum, diesel, or any natural gases. Okay, fuels. Especially they are talking now about the liquid fuels. Okay, so in general they are asking me that talking about the liquid fuels, not the gaseous fuels, obviously. Okay, the gas turbine fuels congeals at -5 degrees Celsius. Okay, to be used in locomotives. Okay. So answer is C. The water soluble salts are also removed from the fuel used in gas turbine. Okay. Okay. This is obviously a true statement. Okay. So now what is the disadvantage of salt? Okay. So the water soluble salts is required to be removed due to chance of surge formation. Okay, which is very harmful for the engine performance. Okay, and it will damage the engine. Okay, because of the salt content. Okay, There will be rust and all these things formation will be there, and the engine will be damaged. I already told, like, this kind of question, lead content should be what? If you don't know anything, just put low. Okay, answer is obviously low. Okay, so why? Because if the lead content is going to increase, the calorific value, which is the most important parameter for a fuel, how much energy it can produce for a 1 kg of fuel bond, which is the definition of calorific value of the fuel, is going to what? Decrease. Okay, if the calorific value is going to decrease, that means the whatever energy it can produce is going to decrease, and if the energy produced by the fuel is going to decrease, that means at the end the efficiency of the gas turbine engine also going to decrease. Okay. So vanadium content increases leads to in decrease in the specific heat of the fuel. Okay, and lead content, lead increase in lead content leads to decrease in calorific value of the. Okay. Then gas turbine engines moves only in dash direction. Okay, this question is very simple, because if you don't know anything, because if you see only in this word when used in any kind of question, okay, 99% of time the answer will be always one. Okay, only in multi-direction we cannot tell, right? And two is also a multi-direction. Okay, so if you don't know anything, also the answer is one. Okay, so now why we just going to see. So now the gas turbine rotates due to combusted gas. Okay, and the gas will flow in what? In one direction. Okay, which are gases and which are flowing in one direction. Okay, so that's the generation. So that means either gases are flowing in one direction, which will whatever the moving parts are there in the inside this gas turbine engine is also going to rotate in one direction, either clockwise or anti-clockwise. Okay, depending on the type of blades, okay, used in the gas turbine engine. Gas turbine engine have dash vibration when compared to reciprocating engine. Reciprocating, the name suggests reciprocating having more moving parts, right? So that means there will be obviously going to be more vibration in the reciprocating part. In gas turbine, there is no moving parts. Okay, only one there is only rotating parts are there. Okay, so that's the reason gas turbine always not produce that much noise. Okay. Which of the following methods can be used to improve the thermal efficiency of open cycle gas turbine plant? Okay, this is all options are correct. Intercooling, reheating, regeneration, all are a kind of different types of processor which are used to increase the combustion efficiency or the thermal efficiency of the gas turbine engine. Okay, so one statement I will give. Okay, just to remember what exactly how it will actually improve the efficiency. Okay. Okay. So intercooling the feed water from the compressor to the turbine and then employing regeneration and reheat to just use the power of the reheated water in order to maximize the power output. Okay, so here actually everything covered in this question. Okay, so here actually you can see one term called intercooling is used. Okay, next intercooling the feed water from the compressor to the turbine and then employing what, then we will do regeneration. Okay, okay, then after that regeneration and reheat both. Okay, and after that to just use the power of the reheated water in order to maximize the power output. Okay, all the terms intercooling. Okay, okay, intercooling, your reheating and regeneration, all terms are used. Okay, all terms are required to increase the efficiency of the gas turbine plant. Okay. The gas turbine is shut down by dash. uh, because the gas turbine requires some fuel to operate, so basically if you cut the fuel, then cut off from the combustor, then there won't be any cycles involving the gas turbine is stopped, and that's the reason it's the gas turbine is stopped operating. Okay. when fuel is got off from the combustor. Okay. Then various processes in the cycle are stopped and then what? Gas turbine is shut down. Okay. What are the major fields of application of gas turbine? All are truth. Okay. Gas turbine can be used in aviation, it can be used in oil and gas industry, and also marine propulsion. Okay. Which of the following is or are the limitation of the gas turbine? They are not self-starting, high rotor speed is required, and it's having high rotor speed, okay, and it's having low efficiency at part loads. Yes, all are truth. Okay, so all these problems we need to improve the efficiency of the gas turbine. Okay. What part or percentage power developed is utilized for driving the compressor? Okay, it's more than 50%. Okay, but now in more than 50%, there is lots of other options. So that is not obviously not nearly to 55. Slightly higher. That is 65% of power is used. Okay, in a gas turbine compressor. Okay. 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 Temperature in gas turbine are about this. It's nearly 2300. Okay, nearly 2300 Fahrenheit. It can convert into Celsius if you want. Okay. Let's see. When inlet temperature is increased to 2600 F, then efficiency is about to dash. Okay. Okay. Even the inlet temperature is going to increase. Okay. That means there is chances of increase in the efficiency of the gas turbine engine, and it can reach to up to 60%. Okay. Obviously, the gas turbine efficiency is also not that much. Okay, but because of high inlet temperature, it can be increased to 60%. Okay. The Brayton cycle with infinite intercooling and reheating stages would approximate a dash. Okay. So let's draw a typical Brayton cycle. In the TH diagram, they are telling a Brayton cycle with infinite intercooling and reheating. Okay. So let's do intercooling, then reheating, intercooling, then reheating, intercooling, then reheating, intercooling, reheating, intercooling, reheating. Add on this, but it can actually go up to what? Infinite. Okay. So then let it be 1, this is 2, this is 3, and this is 4. Okay. 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 Both processes are what? Isothermal process. Okay. Okay. It's called Ericsson cycle. Okay. This is very good and very important term. Okay. This name of this cycle is Ericsson cycle. Okay. The Brayton cycle with multi-stage compression with intercooling and multi-stage expansion with reheating is called Ericsson cycle. Okay, let's come to the problem. We'll see some of the problems. Okay, the question is a closed cycle ideal gas turbine plant operates between the temperature limits of 800 degrees Celsius and 30 degrees Celsius and produces a power of 100 kilowatt. The plant is designed such that there is no need for regenerator. A fuel of calorific value 45,000 kilojoule per kg is used. Calculate the mass flow rate of air through the plant and rate of fuel consumption. Assume Cp equal to 1 kilojoule per kg Kelvin and the ratio of specific heat is equal to 1.4. Yeah. So here I already drawn the cycle. Okay, for the Brayton cycle for the your gas turbine engine. Okay, 2 to 3 there will be a heat addition and 4 to 1 there will be heat rejection. Okay, part 1 to 2 there will be heat input and 3 to 4 there will be heat output. Okay, we need to find out the m dot a and the m dot f. Okay. Okay. So what is your T1? T1 is equal to 30 plus 273 is equal to 303 Kelvin. T3 is equal to 800 plus 273 1073 Kelvin. So T2 is equal to T4 is equal to square root of T1 into T3. Okay. 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 Now when we can apply this equation, the gas turbine with no need for a regenerator. Okay. Okay. So 303, then it is 1073. Okay. So this is your 570.19 Kelvin. Okay. So what? Okay, here on very good statement written. The plant is designed in such that there is no need of regenerate. Okay. Okay. So by that assumption, we can just tell T2 equal to T4 and square root of T1 T3. Okay. And for that also we have actually a formula for your work output. Okay, or the top, most specifically the turbine work. Okay. Okay. So the turbine work WT dot is equal to m dot a Cp square root of T3 minus square root of T1 square. Okay. So this is equal to 100 is equal to m dot a into 1.00 into square root of 1073 minus 303 square root m dot a is equal to 0.423 kg per second. So this is your answer. Okay. Similarly, we know the heat input Q equal to mcp delta T. Okay, which will be your m dot a Cp of a into T3 minus T2. You can see here from 2 to 3 there will be constant pressure heat addition for a Brayton cycle. Okay. So now also this is equal to, we know m dot f Cp. This is very important. Okay, Q in is equal to m dot f Cp T3 minus T2 also is equal to m dot f into Cp. Okay, but because from this relation only you can find out the m dot f if you know the calorific value of the. Okay. We just substitute all these values. These are all the values we have. 423 Cp of air is 1 into 1073 minus 570.19. Okay, m dot f we need to find out calorific value already given in the question, 45,000 kilojoule per kg. Okay, 45,000. Okay, so is 4.7 into 10 to the power minus 3 kg per second. Okay. This is also your answer. Okay. Okay. Let's go to the next question. So the air at 327 degrees Celsius and 4 kilopascal with a volume flow rate of 4 meter cube per second flows through a turbine and exit at 100 kilopascal and 182 degrees Celsius. If the expansion process is polytropic, then calculate the power output rate of heat transfer and rate of change of in entropy, specific heat at constant. Okay, just wait 1 second. Okay, anybody is presenting? Okay, just wait a second. Okay, just wait 1 second. Okay, so this is the question. If the expansion process is polytropic, then calculate the power output, rate of heat transfer, and rate of change of in entropy. Okay. So these are the so some Cp value of air and Cp and gas constant, all these things given. Okay. So yeah, the Brayton cycle I have done on the right. Okay, same Brayton cycle. Okay. Okay, so let's see what are the things given. T3 is equal to 327 degrees Celsius plus 273 is equal to 600 Kelvin. P4 is equal to P1 is equal to 100 kilopascal given. Okay. Similarly, because you see the turbine flows through the turbine and exit at 100 kilopascal. Okay. Exit at 100 kilopascal and 182 degree Celsius, and flows through a turbine. That means inlet is given 400 kilopascal. Okay, and 327 degrees Celsius. Okay, so okay, so so inlet to the turbine is T3. Okay, and sorry, P3 is your what, 400 kilopascal, and exit means your P4, which is 100 kilopascal. Okay, so P2 is equal to P3 is equal to 400 kilopascal. Okay, Now T4 will be your 182 degrees Celsius plus 273, which is 455 Kelvin. Okay. WT we need to find out, and Q bar T we need to find out, and entropy change also we need to find out. Okay. There are three things we need to find out in this question. Because in the question it's mentioned it's a what? Polytropic process. Okay. The process is polytropic. Okay. So whatever the equation we need to apply for the for a polytropic process. Okay. So for polytropic process we need the polytropic index we need. Okay. So first of all we need to find out what is the polytropic index. Okay. So let's consider the process 3 to 4. Okay. As a polytropic process, because 3 to 4 and your 1 to 2 both are the polytropic process. Okay. So T3 by T4 is equal to P3 by P4 to the power n minus 1 by n. Okay. So let's take ln on the both side, and then take n minus 1 by n in on one side. Okay. And all other temperature and pressure terms on one side. Okay. Like ln T3 by T4 is equal to n minus 1 by n into ln P3 by P4. Okay. So n minus 1 by n is equal to ln T3 by T4 divided by ln P3 by P4. Okay. Is equal to ln 600 by 455. Okay. Divided by ln 400 by 100. Okay. N minus 1 by n is equal to 0.1995, implies n is equal to 1.25. Okay. So this is the answer of your n. So yeah, what we will do next, we will find out the m from the ideal gas equation. Okay. Because for the work we need also mass. Okay. Now we're considering it as ideal gas. So for ideal gas, m pv equal to mrt. So m is equal to p1 v1 by r t1. Okay. Everything we have. Okay. 400 into 5 by 0.287 into 600. So m we have 11.616 kg per second. This is m dot. Okay. 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 So yeah, so now let's apply the formula for turbine work. Okay. N by n minus 1 into mr t3 minus t4, okay, which is 1.25 divided by 1.25 minus 1, okay, into 11.616 into 0.287 into 600 minus 455. Okay. So WT we have 2417 kilowatt. Okay. So now one question we have answer. Okay. Okay. So WT we have now. We need next find heat transfer and entropy change. Okay. So the heat transfer in turbine Q dot T. Okay. So Q dot T is equal to gamma minus N divided by gamma minus 1 into N minus 1 into MR T3 minus T4. Yes. So 1.4 minus 1.25 divided by 1.4 minus 1 into 1.25 minus 1 into 11.616 into 0.287 into 600 minus 455. Okay. So if you solve it, you will get Q dot T is equal to 724.72 kilowatt. Okay. Similarly, we have to find out the entropy change. Okay. This is your answer. So let's find the last one. Rate of change of entropy to the gas turbine. Rate of change of entropy through turbine gas turbine. Okay. Delta H T dot is equal to n minus gamma divided by gamma minus 1 into n minus 1. Okay. Into MR ln T4 by T3. Okay. Just substitute all these values. So 1.25 minus 1.4. Gamma is 1.4 for ideal gas or air. Okay, ideal gas as air here. Okay. So 1.4 minus 1 into 1.25 minus 1. Okay. Into M is your 11.616 into R is your 0.287 into ln 455 by 600. Okay. So now if you solve it, that's 1.3832 kilowatt per Kelvin. Okay. This is your answer. Just we will go quickly one question is all. Okay, so all things are similar. Okay, in the simple Brayton cycle, the pressure ratio is 8 and the temperature at the entrance of compressor and the turbine are 300 Kelvin and 1400 Kelvin respectively. Both compressor and gas turbine have isentropic efficiency equal to 0.8. For the gas Assume a constant Cp value and the ratio of specific heat gamma 1.4. Neglect the changes of kinetic and potential energies. Okay, for the power required, find the power required by the compression and thermal efficiency of the cycle. Okay, that means WC and efficiency. Okay, eta hh th of thermal. Okay, thermal efficiency we need. Okay, so let's write down what the things given. So T1 is your 300 Kelvin, RP8 pressure ratio. Okay, and T3 is your what, 1400 Kelvin, eta C is your 0.8 is equal to eta T. Okay, so here actually it's not actually a actual process, it's an isentropic process. Okay, and actual processor are separated. Okay, so that's the reason why there is actually it's not 100% efficient. It's actually given the isentropic efficiency we have is only 80% efficient. Okay, isentropically efficient. Okay, gamma is your 1.4, and also there is no change in the potential energy and the kinetic energy. Okay, okay. So this is the solution. Okay, so WC is your Cp T2 dash minus T1. Okay, so T2 by T1 is equal to Rp to the power gamma minus 1 by gamma. Okay, so what is your T2? T2 is your 300 into 8 to the power 0.4 by 1.4 implies T2 is your 543.43 Kelvin. Okay, so eta C is your T2 minus T1 by T2 dash minus T1 is equal to 0.8 implies 0. Which is equal to 543.43 minus 300 divided by T2 dash minus 300. So by solving we will get T2 dash as 0.4.28 Kelvin. Okay, so we have T2 dash then we have to need to find out the compressor work. WC is equal to 1 into 604.28 minus 300. So WC is here 304.28 kilowatt per kg. Okay, again T3 by T4 is equal to Rp to the power gamma minus 1 by gamma. So T4 is equal to T3 by Rp to the power gamma minus 1 by gamma, which is equal to 1400 divided by 8 to the power 0.4 by 1.4. Okay, so T4 is equal to 772.86 Kelvin. Okay, so what is the efficiency of the gas turbine? Isentropic efficiency of the turbine is T3 T3 minus T4 dash divided by T3 minus T4, which is equal to 0.8 is equal to 1400 minus T4 dash divided by 1400 minus 772.8. Okay, so when you solve it, you will get T4 dash as 501.712 kilojoule per kg. Okay, yeah. So Q dot in is your Cp into T3 minus T2 dash, L1 into 1400 minus 604.28, okay, is equal to 795.72 kilowatt per kg. Okay, Q dot in you have. Okay, let's find out the thermal efficiency of the cycle. Is equal to turbine work minus compressor work divided by Q dot in. Okay. Okay. So yeah, it's actually 501.712 minus 304.28 divided by 795.72. Okay, that is your 0.2481 equal to 24.81%. Okay. So this is your answer. This is also your answer. Okay. Thank you very much for attending the section. If you are attending the recorded one also, thank you very much. If you have any doubt, you can ask in my YouTube channel. Sumit Sagar Hota is my YouTube channel name. Okay. Thank you very much. We will see next week, 6 to 8 p.m. Saturday. Okay. Thank you very much and good night.